Hi, I'm Giorgio Presti from the University of Milan, and I will be your teacher for this lesson, which is entitled Representation of Multimedia Data in the Digital Domain. This lesson will be divided into 4 modules. The first one entitled What is a Signal? The second one from Analog to Digital. The third one is Information Encoding, and the last one is about multimedia files. But before diving into our topic, let's define what does multimedia mean. Multimedia is a form of communication that uses a combination of different contents, for example, text, audio, images, and videos, all together to convey a message. So by extension, a multimedia file should be a file that is capable of holding two or more multimedia elements, for example, video and audio. But practically speaking, we refer to multimedia files when we talk about any file containing other than just text. We can think of audio, images, and videos as signals. So our real question is, what is a signal? A signal can be a continuous variation of values, such as sound, pictures, movements, or a set or finite symbols, such as text, road signs, a pizza menu. And in the second case, those are usually represented by binding some symbol to a conventional numerical representation. But for us, it is more interesting to focus on continuous variation of values. For example, signals as a continuous variation of values can be sound, that is a mechanical perturbation of a medium, a variation of pressure propagating as a wave. Picture, which are a variation of light, basically, or videos that are moving picture, possibly with sound. So let's take, for example, sound, which is the most simple of the signals we saw. Sound, as I said, is a variation of pressure, and it can be depicted as shown in the picture. We have time on the x-axis, and the variation of pressure to the average room pressure values on the y-axis. This is a sinusoidal wave, and we can hear it, for example. As you can hear, it is a very clean signal, which is very artificial. A pure sinusoid wave does not exist in nature. In the case of images, what varies is not the pressure of the room, but is light, basically. So, for example, here we have x-axis and y-axis of a picture, and we can see that when the image is black, the brightness value is 0, and when the picture is full white or very bright, the brightness rises. So if sound is simply a one-dimensional signal, which evolves in time, images are two-dimensional signals which evolves in space. Speaking about sound, let's try to guess how we perceive waves with different height. Can you guess it? It basically corresponds to the volume. For example, signals with very high peaks will be louder, while signal with very low peaks will be softer. Let's hear an example. Another important aspect of sound is the cycle length. As you can see, this sound repeats equal a long time, and the length of one cycle is binded to a precise perception. Can you guess what it is again? It is the pitch, the frequency, the period, the notes played by the sound. Let's hear an example again. As you can hear, long periods of sound are perceived as low frequencies, as low pitch, while very fast repeating sounds are perceived as high pitch. The unit of measure of the volume is the decibel, while the unit of measure of the frequency is hertz. What is frequency? Frequency just mean how many times per second something repeats. And it is the inverse of the period. And what about the shape of your wave? As you can see, here we have one sinusoidal wave with a certain frequency and a certain volume, amplitude. and a square wave with the same peak amplitude and the same frequency. So it will have the same volume and it will be played the same note. But what do you think it's different here? What you can perceive differently? Well, what you perceive is a different timbre, which is basically a different instrument. We can say just a different instrument. And how do you measure the timbre? Let's hear, first of all, let's hear these two waves. You can hear they have the same volume, the same, they are playing the same note, but have different sounds. Unfortunately, this is no easy number to represent the timbre. But fortunately, thanks to Mr. Fourier, we know that any complex signal can be seen as the sum of simpler signals, such as sinusoids, at different frequencies and amplitudes. So it's basically another way to look at the signal. Here we have the waveform, which is the signal evolving in time, while here we have the frequency on the x-axis and the amplitude on the y-axis. This is basically, you can see the spectrum of the signal as the recipe of the signal. To do this sound, we just have to add one frequency at a certain volume. But if we want, for example, to cook this waveform, we must have one sinusoid at this frequency, and some also other sinusoids at different frequencies with different volumes. In particular, this square wave is composed by the fundamental frequency and all its odd harmonics. That means all the odd multiples of the fundamental frequency. We can hear how the sum of different sinusoids build up to create a square wave thanks to this example. Pay attention to the fact that we just add one sinusoid at a time, and at the end of the example, you will no longer hear different sinusoids, but your brain will merge them up into a different sounding wave. The more sinusoids we add up, the more the wave will resemble the ideal shape depicted here. And what about this waveform? Again, it has the same, it plays the same note, so the fundamental frequency will be the same. But in opposition to the square wave, this wave have all the harmonics, both odd harmonics and even harmonics. Let's hear the build-up of this sawtooth wave. Thanks to this Fourier transformation of the signal, we can provide a description of the timbre which is measurable. And what about noise? I mean, noise, it's not repeating himself, and it's random. So to build the noise, we just have to sum all the sinusoids we can produce. As you can see, there is no fundamental frequency, there is no other even harmonics. It's just a mass of sinusoids. And this because there is no repeating module. So as opposed to pitched sounds, noise have a very unpredictable and rich spectrum. It is called white noise because just as the white color, it is made of all the frequencies of a sound. White color is made of all frequencies of light, while white noise is made of all frequencies of sounds. Let's hear a build-up of this noise. Okay? And what if the properties of the signals varies with time? Well, on the upper picture, we have the waveform of the signal seen from a little bit far away, so we don't see the repeating modules. We just see the envelope. Let's call it the envelope of the wave. And here we have a spectrogram or a sonogram of the sound, which have on the x-axis the time, and on the y-axis the frequency. So it's basically like taking this representation and rotating it. So if this representation is in this way, we can rotate it to have the amplitude look toward us. So the third dimension, which is here is represented as a color, is the amplitude. This representation is just like a slice of this graph. And here we can see that there are some peculiar characteristics on the spectral representation of this signal. In particular, here we have an impulsive sound, which is like a short burst of noise, which is visible in the spectrogram as a brief moment with all frequencies present. While on the other hand, here we have some pitched sound, some harmonic sound, and we can see the pattern of repeating harmonics here, and it is probably voice. And as you can see, voice has some pitched components that are vowels, and some noisy components such as S, F, and other letters like them. But if you want to try to see the spectrum of sound, you can go to this website, and I have some cool experiments. For example, this is the spectrum of the voice while I talk to you. I can try to whistle, or we can try to listen to different musical instruments, a flute, or a drum machine, or even some birds. Birds are kiwi. As I said previously, impulsive sounds and non-pitched sounds present a richer spectrum, while pitched sounds have a more horizontal organization of information. So back to our presentation. But which frequencies can we hear, and how many volumes can we hear? In this picture, we can see our hearing space. What this picture tells us is that we can hear any sound above 20 Hertz, which repeated itself above 20 times per second, and under 20 kilohertz, so just the frequencies below 20,000 repetitions per second. But we don't hear all frequencies equally. For example, if we have a 50 hertz signal, it must be quite loud to let us hear it. While if we have a 3K hertz signal, we are quite sensible to that sound. And this is for evolutive reasons, because the crying of baby is concentrated among these frequencies. So for example, speech usually takes up this frequency range and has some dynamic range, which means the difference between piano and forte, the difference between the low volume and the high volume, which is about 30 decibels. Music uses a larger range of frequencies and dynamic range because it's richer. But music does not cover all the hearing space for many reasons. For example, we don't want in music sounds that are too close to the pain threshold, or sounds too low that are not hearable. Keep in mind this picture because we will need this later in this lesson. So just to recap what we saw what is a signal, which is a variation of something, a variation of pressure in time in case of sound, and a variation of light in space in case of pictures. We saw which are the properties of the signals, So for example, the amplitude, which is the volume for sound or the brightness for pictures, and the frequency, which is the pitch for sounds, or basically the size of the features of a picture. We also saw how to represent a signal in a different domain, which is the frequency domain, which is somehow a recipe to generate the waveform or the shapes in images. And we saw which is the space of the sounds we can perceive, which is useful later. If you missed something of this, please watch the lesson again until now.